Hello, this is Mr. Springer again. We've got a short video, hopefully short, on solutions and stoichiometry and that sort of thing. So let's dive right in. A solution, of course, is a homogeneous mixture of two or more substances. Now you got to think back a little bit, because all matter is either a substance or a mixture. And elements and compounds are examples of substances. They have a set formula. They're always the same. Elements are things like carbon, hydrogen, oxygen, things like that. Things that you can find on the periodic table. And then compounds are made of elements, so they are things like bleach, sugar, water, okay? And they have common names, like I just said there, but it's actually sodium hypochlorite, sucrose, and, water. But the commercially available products generally not as pure as you might want for doing a lab in chemistry class. So everything else is a mixture. There are a couple of kinds of mixtures. A mixture that looks like a mixture. It's called a heterogeneous mixture. You can pick out the parts of the mixture. You can see the different things in the mixture. Like Lucky Charms, right? You can pick out the different charms, and I think the cereal pieces themselves are different shapes. Or trail mix, you might have raisins or peanuts or whatever you're not allergic to in your trail mix, and you can just separate them by just picking out the different pieces. It looks like a mixture. A mixture that doesn't look like a mixture is called a homogeneous mixture. You can't see the different substances. You can't tell what's in it, okay? So like black coffee, Kool-Aid, things like that. Things that just look the same all the way through. If you didn't know better, you would think they were just one thing. So there's two parts to a solution. Solute, which is the substance that gets dissolved. And the solvent is the substance that does the dissolving. And most of the solutions that you're going to encounter in high school chemistry labs will be aqueous or aqueous. I'm never sure how to pronounce that. Solutions. An aqueous solution has water as its solvent. And so what could be dissolved in water? Well, you might have a solid dissolved in water, like salt or sugar. You might have a liquid dissolved in water, like, I'm thinking maybe we'll say vinegar. It's got acetic acid dissolved in the water. Or gas, like carbon dioxide, could be dissolved in water. If we open a can or a bottle of carbonated beverage, it has carbon dioxide dissolved in it. As soon as you open it up, that comes out of solution. But while it's sealed, the carbon dioxide is dissolved, and it is a solution at that point, I believe. Other solutions, which are not liquid-based, brass is a solid solution. It's a mixture of zinc and copper, I do believe. And air at room temperature, that's a gaseous mixture, homogeneous mixture, mostly nitrogen gas and oxygen gas. And there's some other stuff in there. Everybody, if you're in the room, you're breathing out some carbon dioxide, but that's a pretty small percentage of the air in the room. It's like 78% nitrogen, 20% oxygen. So that's 98%, 99% there, depending on whether it's 20 or 21 on the oxygen. And so it doesn't really matter where you are in the room. It's not like there's a pocket of oxygen somewhere and short on oxygen other places. It's pretty much the same all the way through. So those are some different examples of types of solutions. And remember we said that the solute is a substance that is dissolved. There's generally less of it, and the solvent is what does the dissolving, and there's generally more of that. So if you're not sure, whichever one you have more of is the solvent, whichever one you have less is the solute. And these are not exact terms of measurement. It does make a difference how much you put in. I was wanting to make 3 mixtures of copper 2 sulfate solution, but I think my water must be bad because they turned out cloudy. But I was going to put a different amount in each one, and you could tell a difference in the color, which one had more stuff dissolved in it, because the copper sulfate makes a blue solution. So if you're making Kool-Aid or something like that, a drink mix, the envelope requires addition of sugar. I think it's usually a cup of sugar. What if you only add a teaspoon? How's that going to taste? Probably not very good. If you've ever had Kool-Aid made by someone who was saving on sugar or trying not to have sugar, you can get some pretty bad Kool-Aid out there, so be careful with that. So we need a way to measure concentration of our solutions in such a way that we can use them in chemical reaction to do stoichiometric calculations with them. And there are several concentration units that you might come across. Percent, there's percent by volume, percent by mass, but it's percent. You're familiar with the term percent. That means per 100, right? Percent per 100. One you might be less familiar with, parts per million, which is like percent, only instead of 100, it's per million, or parts per billion, same idea. And those are generally things that are bad, like pollutants, are often measured in parts per million or parts per billion. You're only allowed so many parts per million lead in your drinking water, or maybe it's parts per billion, I don't know. But it's a very tiny piece that is allowable. Anyway, molarity, which is symbolized with a lowercase m underlined, would be more in line with what we would want to use in a lab class, because it has moles of solute, but it's per kilogram of solvent, so it's how many moles dissolved in the mass of water that you use to dissolve it, which is a little bit more difficult to do. I mean, it's not hard to do, but it's a little more time-consuming to try to weigh out your solvent. What we do like is molarity, which is a capital M underlined, so be careful with that, not the lowercase, but the capital M. There is a difference. And molarity is moles of solute per liter of solution. Now, once again, I'd like you to pay attention to the differences. Molality is moles of solute per kilogram. Oh, why is that color? Per kilogram of solvent. And molarity is moles of solute per liter of solution, which brings us to the other difference, solvent versus solution. So we're just going to add water to get to that liter if we're doing molarity, and that'll hopefully become more clear as we go along. So molarity, like I said, is probably the most commonly used concentration unit, at least in high school chemistry. And so how would you make 100 milliliters of a 0.33 molar sodium chloride solution? Well, you're going to need a balance to measure your NaCl, a 100 milliliter volumetric flask, which if you've not ever seen one of those, that's a pretty handy piece of equipment to have. You can look that up if you have not seen one. You're going to need some sodium chloride. Sorry about the bell. Sodium chloride and some distilled water. And so then step 1, how many moles of NaCl do you need? Right, we're trying to make a 0.33 molar solution. And so we need to know how many moles that is. Well, we've got 100 milliliters, which if we need that into liters, so 100 milliliters would be 0.1 liter. And we want it to be 0.33. Remember, molarity means moles per liter. So 0.1 times 0.33, 0.033 moles NaCl is what we require. Get to the right page here. Okay. And then how many grams would that be? Well, we'll take our 0.033 moles of NaCl, and just like we've done in the past, we're going to convert that to grams of NaCl. So we're going to multiply by the molar mass, 58.44 grams is 1 mole. And so that turns out to be 1.92852. We started with 2 digits. We should end with 2 digits, I believe. So we could say 1.9 grams. Our scales, though, will go 2 decimal places, so I might try to get to 1.93 if I'm doing that in the lab. So we're going to measure out 1.93 grams using the balance. We'll put that in the volumetric flask. We're going to add enough water so we can get it to dissolve, and then add it the rest of the way up to the line. And that takes care of that. That's how you make that solution. If you have 100 milliliters of 0.33 molar NaCl solution and you take 10 milliliters of it out to use in a chemical reaction, the concentration of the 10 milliliters that you took out is still 0.33 moles per liter. Even though you've only got 10 milliliters of it, it's still 0.33 moles per liter. Concentration is kind of like density. It doesn't matter how much you've got. As long as you know the concentration of the piece you broke it off of, you've got the same concentration. So you didn't add any water to dilute it. You didn't remove any water to concentrate it. You didn't add or remove any NaCl to change the concentration. You simply took 10 milliliters of the solution from one container and put it in another. So how many moles of NaCl are in that 10 milliliter sample? Well, 10 milliliters is 0.010 liters. And we know it is 0.33 moles per liter. So 0.0033 moles. All right, so here's a problem, a stoichiometry problem now. 10 milliliters of 0.33 molar NaCl solution mixed with excess lead nitrate solution, lead 2 nitrate solution. Excess, so we don't have to worry about how much of that we've got. How many grams of precipitate can be made? We're looking for the theoretical yield here. So we're going to have a balanced equation. We're doing stoichiometry. Sodium chloride plus lead 2 nitrate. This is, of course, you recognize this as a double replacement type reaction. So I'm going to have some lead 2 chloride, right? Lead 2 has a charge of +2, chloride has a charge of -2, so I'm going to take 2 of the chlorides. And sodium nitrate. And we need to balance that equation just for the sake of time. I know I've got 2 chlorines here, so I better have 2 NaCls. If I've got 2 Nas and 2 NO3s, I better have 2 NaNO3s. So there's my balanced equation. I'm going to remove those charges. It's my balanced equation. We need to figure out which one of those is the precipitate. Well, lead, mercury, silver are always in the precipitate. So there's my precipitate. That's what I'm trying to find. So I'll take my 10 milliliters times 0.33 moles per liter. Now, find over given 1 mole PbCl2 over 2 moles NaCl. Remember the 1 from here, the 2 from here. And then we need the molar mass of that. I just happen to go ahead and calculate that. That's 278.1 grams PbCl2 in 1 mole. Canceling everything that'll cancel. I end up with 0.46 grams PbCl2. Started with 2 digits, end with 2 digits. That's sig figs. All right. And we got one more page here. Here's a molarity hack. I invented this. As far as I know, I've never seen anybody do this. I've seen it with other things like density, but here's the triangle. You cover up the thing you're looking for and do the math that's left. So if you're looking for moles, you cover up moles and you multiply molarity times liters. If you're looking for molarity, you cover up the big M and you got moles divided by liters. If you're looking for volume, you cover up the liters and you got moles divided by molarity. So let's see what happens here. What volume in milliliters of 1.25 molar, that's the molarity, calcium chloride solution, is required to get 0.20 moles of CaCl2. So we're going to cover up liters. That means we need moles over molarity to do the problem. So I'm going to take my moles and divide that by my molarity. And that would be the same thing as 0.20 moles divided by 1.25 moles over 1 liter. And when you divide by a fraction, you multiply by the reciprocal of the fraction. So 0.20 moles times 1 liter over 1.25 moles. And so my moles are canceling there. They would have canceled here too. But I get, as my result, 0.16 liters, which it wanted it in milliliters. So I'm going to multiply that by 1,000, 160 milliliters. Okay, so that takes care of that. Like and subscribe if you haven't already, if this helps you. And I will see you next time.